Hi, everybody. This is Miss Weeson, and this is the third podcast of Unit 2. Right now, we're at the bottom of page 7, and today we're going to learn about covalent bonding and structure, but more specifically, we're going to do a review of how to do Lewis dot structures. So, we're going to use this model called the localized electron bonding model, and this is going to help us understand the nature of molecular bonding. And in particular, this model is going to assume that molecules are going to be composed of atoms that are bound together in such a way that there is a sharing of valence electrons through the use of the atomic orbitals we learned about in last unit. And remember, the atomic orbitals we learned were s, p, d, and f. And ultimately, the last thing before we move forward, especially when we do Lewis dot structures, is it's important to remember that one bond equals a pair of electrons. And what is a pair? Two. So 2 electrons. And in this podcast, that's really what we're going to focus on. We're going to focus on Lewis dot structure. And then later on in future podcasts within this unit, we're going to learn how Lewis dot structure actually helps us predict the molecular geometry and shape of the actual substance. And we're going to use something called the Vesper model. And then towards the end of this unit, probably in our last podcast, we're going to look at a phenomena that occurs when atomic orbitals start to blend in and overlap with each other to create something called hybridization. Before beginning, you guys learned the octet rule. Remember that, the octet rule. 8 is great, or we even say noble is good. And why do we say noble is good? That's because the noble gases have 8 valence electrons. That ensures maximum stability of the molecule at the lowest energy states. So, do you remember hearing about single bonds, double bonds, and triple bonds? Well, let's go ahead and review here in a little bit more detail and add some new language that you may not know. Again, a single bond between 2 elements is meaning that they're sharing one pair. And remember, a pair is 2. So they're going to share a pair of electrons between those 2 elements to form that single bond. But now, since we're in advanced chemistry, we're going to call that bond a sigma bond. And we will use this symbol over here, a lowercase Greek symbol, I believe. So if I could just draw a generic example and have one element single bond to another element, then I know that bond is called also a sigma bond. And we're sharing one pair of electrons. A double bond, as you probably can make a guess, is when 2 elements are sharing 2 pairs of electrons between the 2. And so again, if I were to use just kind of the same notation and show a double bond forming between 2 elements, we know that the first bond is always going to form, will be called the sigma bond, but now this double bond is called a pi bond. And lastly, we're going to have a situation where elements can actually share 3 pairs of electrons between the 2 elements. And the first shared pair would be the sigma bond. The second and third shared pair we would refer to as a pi bond. It's safer to say when we see sigma and pi bonds together that they're stronger than just a sigma or single bond alone. However, pi bonds are going to be weaker than a sigma bond, but will never exist by themselves. I like to use a general example, and what we could do is just title it here in the notes. I'm going to write on the side, so please feel free. I know that I didn't leave you much space, so you're probably taking notes in a notebook. But this will go with the disclaimer that I listed here in bright yellow. It says that multiple bonds increase the electron density between the 2 nuclei of elements. And when that happens, there's going to be a decrease in repulsions while you have an increase in attraction. And so what ends up happening as you increase the bond, those 2 nuclei are going to move closer and closer together. And so the bond length is actually going to get shorter for double bonds, more so than a single bond. But a triple bond, you guys, is the shortest of them all. So one more thing I'd like to tell you before we do a review of Lewis dot structure is this phenomena of a formation of something we call coordinate covalent compounds, okay? And a coordinate covalent compound is going to form a coordinate covalent bond. Now, this is just when you have certain atoms like nitrogen and phosphorus. These aren't the only ones, but there are others. And what happens is they tend to share a lone pair with another substance or element floating around that is short of electrons. And so the attraction will actually force them to create a coordinate covalent bond. All right, and I have an example here in our notes that, it's kind of hard to see, but there's an arrow here. So everything to the left of the arrow are the reactants. And so we're starting off with NH3, which you guys, we call ammonium. And you can see what happens here. Ammonium has this lone pair hanging out on the central nitrogen atom. And that lone pair, which by the way are electrons, is going to be overall negatively charged in this area. And when, for example, a hydrogen proton, which I just circled here, is lacking an electron, that's why it has a +1. So hydrogen here is lacking an electron. It's actually going to be attracted to that lone pair on the nitrogen of the ammonia molecule. And so consequently, what ends up happening, and to the right of the arrow, is an ammonia molecule forms, which is now NH4 plus. Okay. And so what you have here that I've highlighted in yellow where that arrow is, that is technically that covalent, coordinate covalent bond that forms. And you can see hydrogen here is kind of a freeloader and is getting that bond for free, if you will. Real quick, another example, there's many, but just off the top of my head, another example of a coordinate covalent compound that forms is between, again, ammonium, NH3, and another non-molecular compound called boron trifluoride. And in order to understand how this happens, you need to know how to do Lewis dot structure. And we're getting ready to review it, but let me show you really quick what happens. You have NH3, its Lewis dot structure looks like this, with that lone pair sitting on the nitrogen. And then boron is going to have a Lewis dot structure that looks like this. Okay, really quick, draw your attention to boron. Right now, it only has 3 bonds to it. And we learned that 1 bond equals 2 electrons. And so if it has 3 bonds, that's only 6 electrons. And remember, every element wants an octet. And so what's going to happen here is this lone pair on nitrogen is actually going to be attracted to that boron, and a coordinate covalent bond will form. Okay, let's review how to do Lewis dot structures. Now, I'm really depending on the fact that you've seen this before. And what I've done is I've generally outlined in 7 steps how to do and determine the Lewis dot structure for compounds. I will tell you that you won't necessarily use every single step depending on the problem that you're doing. I would like you to pause me right now and you can read these steps one by one individually. I'll do a really quick synopsis of them, and then we'll just go ahead and jump right into some examples while it's fresh in your head. All right, I'm going to highlight some things in these steps that I think you should know and you should follow along with me, starting with step 1. Hydrogen's always going to be your terminal atom, or the atom that's written at the end or the outermost. Remember, hydrogen can only make one other bond, one other connection. Can't tell you how many times I will see a student try to create, for example, like a double bond around hydrogen, or sometimes they'll create a bond and write a lone pair around hydrogen. Hydrogen can only make one connection with another atom, okay? The second thing you need to know when doing Lewis dot structure, if you're dealing with multiple elements, you have to determine which one has the lowest electronegativity. And when writing your Lewis dot structure, that one is going to be the one you write centrally, or the one in the middle. Okay, use the electronegative trends that you learned last unit to inform you which element will generally be more electronegative than another. The next thing you're going to do is you are going to figure out how many electron pairs you have to draw for the Lewis dot structure. Okay, there's a little formula here that we use. What you're going to do is you are going to find the elements that you're drawing the Lewis dot structure for. You need to determine what group number they are in. That group number tells you the number of valence electrons. And so what you're going to do is you're going to add up the total number of valence electrons for each element. You will then divide that by 2, because once you do that, that's how many electron pairs you will need to draw into your Lewis dot structure. Okay? Ions, don't forget, if it's a negative ion, negative means it's taken on more electrons, so you're going to need to add accordingly. Whereas if it's a positive ion, remember that it's lost negative charge, so you would have to subtract accordingly. In step 4, once you're done determining the electron pairs, you will then simply just create a single bond, or if you will, a sigma bond, between each element or each atom that's bonding in that compound. Don't forget to subtract that from the total that you just determined in the previous step up here, because that's going to give you guidance on, letting you know when you're done drawing the Lewis dot structure. When you are getting to the point that you have created a single bond between every bonding atom in that compound, you will then place lone pairs of electrons around the terminal atoms. So any other atom at the ends of these molecules that do not have an octet already, you will literally put lone pairs there. One more time, except for hydrogen, because you can only form one bond, okay? There's a special note here that you might not have learned in first year chemistry. I will tell you that if your central atom in your Lewis dot structure is an element that is a part of the third period or higher, so the third row or higher, it can actually accommodate more than 4 electron pairs, but actually can accommodate up to 6. Last step, if you end up having any extras and the central atom does not yet have 4 electron pairs, what I'm going to say is that you will need to then create double bonds or triple bonds. So you'll need to create pi bond pairs. Word of the wise, really not every element on the periodic table can take a double or triple bond. In fact, it is pretty much only carbon, nitrogen, oxygen, phosphorus, and sulfur that, when bonding with each other, can form double and triple bonds. I do have some more notes here on exceptions to the octet, but I think it's more important we actually practice the steps that we just went over. And so what I did, if you go ahead and go to exercise 8 on page 9, I have, to the right side of my exercise practice problem, I have generally created the steps that I had written in my notes above. Now, you'll see that I just really quickly generalized the steps into short little snippets so I didn't have to rewrite. And that might help you, because when the steps get too wordy and too lengthy, it can feel a little overwhelming. So let's use the steps that we just learned to determine the Lewis dot structure for some of these compounds in exercise 8. Let's start off with HF, you guys. That is hydrofluoric acid. And there's only 2 elements that make this substance up, a hydrogen atom and a fluorine atom. And so right now, if you look at step 1, hydrogen's always going to be terminal. Well, yeah, of course it is, because if I'm drawing the Lewis dot structure for hydrogen and fluorine, and there's only 2 elements, then of course one will be terminal. Okay, take a look at step 2. It says that the element with the lowest electronegativity is going to be the one in the central. Well, obviously this step doesn't really apply because there's only 2 elements in hydrofluoric acid, HF. All right, so step 2, don't really have to do that for this one. Step 3, determine the number of electron pairs. Remember how we did this. Go back up to the notes if you can't, but what you are going to do is determine the number of valence electrons in each element. And to do that, Just go to the periodic table and see the group number it's in. So hydrogen is in group number 1 and fluorine is in group number 7. So we're going to add the total number together to get 8. And last step is we then divide by 2. And so what we're going to get for this first one is we have to account for 4 pairs of electrons that we are going to need to draw within this Lewis dot structure. And when we draw a pair of electrons, we can either do it through a bond or drawing dots around the element. So in the case of hydrofluoric acid, and right now you guys, we're actually on step 4 of our notes, step 4 of the process rather. It says that we are going to place a sigma bond or a single bond between the atoms that are bonding. And in this case, hydrogen and fluorine, there's the single bond. Question, can hydrogen take any more electron pairs or any more bonds? No, it could only form one bond. But guess what? Since we drew one bond, I now no longer have to account for 4 pairs of electrons, but now I have to account for 3 pairs of electrons. Now I take a look and I realize that fluorine does not have a full octet. In fact, right now, when it's bonded to hydrogen, it only has 2 electrons. Remember, they share electrons. So how can I account for 3 pairs of electrons around fluorine? Well, that's when you will simply draw 2 dots on either side of the element. And so right now, we are pretty much done here. Each element has a full octet, and in the case of hydrogen, it has a duet. We've accounted for all 4 electron pairs, and that would be it. Okay, let's go to the next one. N2. Now this one I'm going to also kind of indicate to you guys there's only 2 nitrogen atoms here. So clearly the first step, hydrogen is always terminal. That won't apply here because there's no hydrogen. And step number 2, the lowest electronegative element is going to be in the middle. Well, there's only 2 elements here. There's 2 nitrogen atoms. So that's not going to really matter either. Now we are on step 3 now. We have to determine the number of electron pairs that we have to draw in this Lewis dot structure. How do you do that? Go to the group number nitrogen is in, which is 5. That means each nitrogen atom has 5 valence electrons. And since there are 2 nitrogen atoms, then I have to account for a total of 5 pairs of electrons. Don't forget to divide by 2. So in my drawing, in my Lewis dot structure, I have to account for 5 pairs of electrons. Now I'm on step 4 over here. I have to place a single bond between all bonding elements. Well, here it is. There's one. Okay, so now I no longer have to account for 5 pairs of electrons. I have to account for 4 pairs. So I have to get that 4 down to 0. Now, what you're going to realize is that when you draw the remaining 4 pairs, it's going to be a real challenge. I'll just show you to make nitrogen have a full octet. So if I put a lone pair, that would be 1 pair, 2 pair, 3 pair, and 4 pair. Do you think that this would be the Lewis dot structure for N2? Take a look at each nitrogen. Does each nitrogen have an octet? No, they don't. So clearly this would not be the Lewis dot structure. Now, if you go to step 6 in our notes here, or in our little guide to the right, it says that if that central atom is not, or if the atoms are not surrounded by an octet or 4 pairs, then that's when we want to start creating double and triple bonds. So remember, I still have 4 pairs of electrons I have to count for. So what if I were to do this? Here's 1 pair. Now I'd have to account for 3. Here is another pi bond. Here's another pair of electrons. So now I would have to account for 2. And stop before you move even any further. How many electrons does each nitrogen atom have at this moment? 6, right? Each one has 6. Well, if I have to draw 2 more pairs of electrons, wouldn't it make sense then if I drew a pair on this end of 1 nitrogen and a pair on the other end of nitrogen? Now ask yourself, how many electrons are surrounding each element? And now you would say there are 8 electrons surrounding each element. So that, in fact, would be the Lewis dot structure for N2. You would have to go in and create pi bonds. NH3, letter C, rather, in exercise 8. So we know hydrogen is going to be terminal. It can only form one bond. Now look at step 2. It says the lowest electronegative element is going to be central. Well, we know that nitrogen, in this case, NH3, nitrogen is actually more electronegative than hydrogen. But what did we just say? Hydrogen can only and always will be terminal. It's always going to be written at the end. So this is an exception where we don't necessarily put the lowest electrical negative atom in the middle. That's because it's surrounded by 3 hydrogen, and we know the hydrogen has to go at the end. So really quick, if I have 1 nitrogen and 3 hydrogen, you can draw it like this. If you wanted to draw it like this, you could also write it like this, or even like this. So right now, where exactly you are putting those hydrogens isn't a huge deal. We're trying to make sure we are accounting for the correct bonding structures and the correct number of electron pairs. So let's go to step number 3. How many electron pairs are going to end up being in a molecule of NH3? Again, group number for hydrogen is 1. Group number for nitrogen is 5. And so I'm going to just do and show you over here, 3 hydrogen, 1 times 5 is 8 electrons. Do not forget to divide by 2 because that will tell you how many pairs that you have to account for. And it looks like I'm going to have to account for 4 pairs, 4 electron pairs when I draw my Lewis dot structure. So then go to step 5. You're going to, now you're going to go to step 4 and create your single bonds between all participating atoms. So 1, 2, 3. Subtract that from your total pairs. So now I only have to account for 1 pair. Well, go ahead and ask yourself, where will this pair go? Well, I'm not going to create any more bonds with hydrogen. I can't put any lone pair of electrons with hydrogen because it can only create 1 bond. But take a look at nitrogen. Right now, how many electrons is it bonding with? That's right, 6. What does it want? It wants 8. So since we have to account for 1 more pair, we would simply put that pair right here. And now every single atom in this compound is fulfilling the octet, or in hydrogen's case, the duet rule. Okay, let's go ahead and go on down to CH4. I'm going to go ahead and always note that hydrogen is terminal, and therefore carbon is going to end up going in my middle by default. Okay, so there's the preliminary structure. Now we have to actually do the math, and that's step 3. How many electron pairs are we going to have to draw? Well, you need to know the group number, and that will pretty much tell you. So I have 4 hydrogen, each with the group number of 1, and then carbon is in group 4, and there's only 1 carbon. So how many electron pairs will you be responsible for drawing in? 4 pairs. And remember, an electron pair can be a lone pair or an actual bond. So now we are on step 4. Place the single bond between all atoms participating in the Lewis dot structure. 1, 2, 3, 4. And actually that we account for all 4. So now we're done there. So this would be the Lewis dot structure for CH4. Let's try CF4, okay? CF4. And I know that the organization here is a little wompy, you guys, so I'm just going to kind of write over in this space to the right. Hydrogen's always terminal. That doesn't apply here because there's no hydrogens in this atom. So go to step 2. The lowest electronegative atom is central. Which one between carbon and fluorine, you guys, has the lowest electronegativity? You should instantly say carbon, and that's because you should know fluorine is the most electronegative atom. So generally speaking, I'm going to have carbon in the middle with fluorine surrounding at the terminal ends. Okay. Now we need to determine the number of electron pairs we are responsible for drawing in. How do you do that? Group number. So fluorine, there's 4 of them. And if I go to fluorine, it's in group 7. And since there's only one carbon atom and its group number is 4, when I do the math, I get 32. Do not forget to divide by 2 to determine the number of pairs. And then that means I have to account for 16 pairs of electrons around this CF4 molecule. So we're now on step 4, you guys. Place the single bond between all participating atoms. And there's one, there's one, there's one, and there's one. And you guys, I started off with 16, but I just drew 4. So now I have to account for 12 more pairs. So here's how you always need to think of it. Look at carbon. Does carbon have an octet? Yes, it's got 4 bonds. Each bond has 2 electrons. Carbon's good. What about fluorine? Right now in our Lewis dot structure, each fluorine atom only has 2 electrons. So I need to account for 12 pairs. Well, when I draw a pair, I usually do 2 dots like this. That's 1 pair, 2, 3 pair, 4 pair, 5, 6, 7, 8, 9, 10, 11, and 12. And so each one of my elements in a molecule of CH4 has fulfilled the octet rule. I've accounted for all pairs of electrons that I determined I needed to draw. Okay, let's do one more F, NO+. So this is a cation. Please don't mind. I'm going to go ahead and erase some of this here to create some space for this one. Okay, and I might have to kind of just go down in the margins a little, so I apologize. Now, I'm hoping you're really getting used to kind of following these steps at this point. It is a matter of repetition for something to become really comfortable and familiar, so you need to be practicing Lewis dot structures. Okay, right off the bat, hydrogen's always terminal. That doesn't matter here because there is no hydrogen. And then you're going to look at step 2. There's only 2 atoms, you guys, so it's not like you're going to place one in the middle since they're going to just be side by side. Number 3 is where we start. Determine the number of electron pairs. Well, there's one thing that you have to realize in cations, okay? When you see a +1 here, how many electrons has it lost? Remember, when we lose negative charge, it becomes a cation. So we've lost 1 electron. So when we go to do the math in step 3, we need to be certain that we account for that. So nitrogen and oxygen. Nitrogen, really quick, is in group number 5. And then oxygen is in group number 6. But because we are losing an electron, I would say that we would knock that down by 1 to 5. So 5 plus 5 is 10. Don't forget to divide by 2 to determine how many electron pairs you have to be responsible for. And that would end up being 5 pairs of electrons that you have to draw. Nitrogen and oxygen are going to be right next to each other. So place your single bond first. Now I have to account for 4 electrons and 4 pairs of electrons rather. So how would you do this? How would you create and put 4 pairs of electrons around nitrogen and oxygen to where they would both have an octet? My guess is you're really going to struggle. And when you get to this point, that is when you're going to look at step number 6 and start considering double and triple bonds. This is when you need to start creating pi bonds. So if I have 4 more pairs of electrons to account for, tell me if you agree with this. 1 pair could go here. 1 pair could go here. And now look at nitrogen and oxygen, you guys. Each of them only have 6 electrons. They want 8. And since I have to account for 2 more pairs, couldn't I put 1 right here and 1 right here? And then it looks like both elements have a full octet. One more thing, when you see Lewis dot structure for ions, I would expect that you put a bracket and then you put the charge of that Lewis dot structure. Okay, does that help a little bit, you guys? I'm hoping there's going to be enough practice that this would become second nature to you. Now, I'm going to have you crawl back up here to the top of page, or excuse me, to the bottom of page 8, and there's some critical information that you probably didn't learn in first year chemistry, and these are exceptions to the octet rule. Number one, we learned that 8 is great, an octet is happy. But we also learned that hydrogen and helium, that inner shell, can only take on 2 electrons. So hydrogen and helium, and even lithium and beryllium, are going to take fewer than 8 electrons. The element that is less than element number 5 can have fewer than 8. Exception number 2 is the opposite. These are elements that can have what we call an expanded valence, or rather a valence shell that can actually take on more than 8 electrons, or if you will, 4 pairs. So another way to think about this, you guys, is if you look at the periodic table and you look at rows 3 through 7, those elements can actually take on more than 4 pairs. They can actually take up to 6. Last but not least, odd number electron compounds. So there's going to be a few compounds that are going to contain an odd number of valence electrons in their shell. And so by virtue of that, they would never be able to fulfill the octet rule. These are just a couple I list here. Let's take a look at exercise 9, which is going to help us kind of highlight some of those exceptions we quickly went over. It's wanting us to draw the Lewis dot structure for phosphorus pentachloride, or PCl5. And there's no hydrogen atoms here, so there's obviously going to be no terminal hydrogens because there is none. Now, which of these elements, phosphorus or chlorine, is least electronegative? If you said phosphorus, you are correct. Now, take a look at where phosphorus is. Which row of the periodic table is it in? It's in the 3rd row. And remember, go back up here. Elements that are in rows 3 through 7 can be surrounded by more than 4 pairs of electrons. Yes, in this example, phosphorus is in the 3rd row and can therefore take on more than 4 bonds, or 4 electron pairs. So chlorine consequently is going to surround this phosphorus atom. And you still need to add up the total number of valence electrons and divide by 2 to get the total number of pairs. And since phosphorus is in group 5, there's only one of them. That'll be 5 electrons. We've got 5 chlorine atoms. They're each in period 7. So when I do the math here, I get a total of 40 electrons. I divide by 2 to get how many pairs I need to account for. Wow, so I need to account for 20 pairs of electrons. In the whole time I'm doing this, I'm realizing that phosphorus can have an expanded valence shell. It could take on more than 4 bonds. And so what I'm going to do then is I'm going to create 1, 2, 3, 4, 5 bonds between the phosphorus and chlorine atoms. Keep track. Go back over here. Since I've drawn in 5, I only have to account for 15 more only. Now, phosphorus, since its expanded valence can take on 4 or more, and in fact it has, it's taken on 5 bonding pairs of electrons. And at this point, I'm going to make the assumption that the shells of phosphorus are completely full. So where am I going to put these 15 pairs? Remember, a pair equals 2. And each of these chlorine atoms needs to also have a full octet. And right now, each chlorine atom only has 2 because of the bond it's creating with phosphorus. So what if I did this? And I'll do this in a different color. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Bam. Let's try a couple more. Lewis dot structures for molecules that violate the octet rule. So again, we're going to be looking at more examples that are exceptions to the Lewis dot rules we went over to begin with. Let's take a look at chlorine tetrafluoride. Obviously, in this particular case, chlorine and fluorine, which one of those has the lowest electronegativity? They're close, but it's chlorine. So chlorine is going to go in the middle. It's going to be the central one. And then fluorine is going to go around and bond to chlorine in such a way that we're getting ready to determine. And so we need to figure out and calculate the number of electron pairs. And so go to your group number, and chlorine is in group number 7. And then since there's 3 fluorine atoms, they're also in group 7. This gives me a total number of 28. I divide by 2 to find out that I need to account for 14 pairs of electrons. Then you create initially your sigma bonds, 1, 2, 3. And now I have to account for 11 pairs. So make sure you keep track. If you keep track of how many pairs you've drawn in versus what you have to do, this will definitely help you. Okay, so what else is going on here? I'm going to ask you to tell me, where is chlorine found on the periodic table? What row is it in? That's right, it's in the 3rd row. And we learned, let's go back up, you guys. We learned that elements in periods 3 through 7, or rows 3 through 7, can have an expanded valence. And it looks like that's exactly what's going to happen to chlorine here. But before I do that, I know that I'm going to have to draw in 11 pairs of electrons. Right off the bat, I'm going to go ahead and fulfill the octet rule for the fluorines that are there. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so now I have 2 pairs I have to account for. And those 2 pairs, since chlorine can take on an expanded valence, those 2 pairs will actually go around the chlorine, central chlorine atom. Okay, let's try another one. B, xenon and oxygen. Xenon trioxide. Both of those, there's no hydrogens there. Let's go ahead and determine which one is central. That would be xenon because it's the least electronegative. So I'm going to just draw an arrow over here, Xe, and I know that the oxygens are going to go and surround the central xenon atom. Find where xenon's at. Hey, is xenon in periods 3 through 7? Yes. Xenon is a very large element and can take on an expanded valence. In other words, xenon can take on more than 4 bonds or 4 shared electron pairs, if you want to say it that way. Let's do our math real quick and find out how many bonding pairs we have to account for. Xenon is in group 8, and then since there are 3 oxygens, and each oxygen is in group 6, I do the math. I get 26 and divide it by 2 to determine the pairs I need to account for, which it looks like 13 pairs. And within those 13 pairs, I'm going to start off by creating my sigma bonds between all players. And now I have to only account for 10 pairs. First thing I'm going to do is I'm going to make sure each of my oxygens has a full octet. So I'm going to put a pair here, 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 and so on and so forth. Okay, how many pairs did I just draw in? I just drew in 9, right? So I have 1 pair to account for. Wait a minute, xenon can take on an expanded valence, and therefore that other lone pair will be on that central atom. All right, I'm hoping that this is becoming a little bit more clear as we do more practice. It looks like C, D, and E, I'm going to let you try on your own. You will notice there was no answers here because it's hard to port the answers in Lewis dot structure. However, I would be happy to go over these in class as exceptions to the octet rule. Okay, we're going to stop here, you guys. Thanks for your patience. Thanks for your review. Let me know if you have any questions.